Hey everyone, sorry I couldn't be there today. Today we're going to start our next unit, simple harmonic motion. It has a lot to do with energy, although today's lesson won't, so that's why we're kind of doing it together with energy. Let's go. Simple harmonic motion. So we're going to start with a definition that's a little more technical than probably what you guys need to know. Simple harmonic motion is anything that oscillates where the restoring force is proportional to its displacement. Okay, so kind of a technical definition there. Restoring force is the force that takes something and puts it back sort of where it belongs or back to its original position. And sort of the big term here that we need to be familiar with is oscillates. Oscillates it's kind of like a fancy science word for go back and forth, really. So we're looking at objects that go back and forth. Because what's the point of being good at science if you can't use, big fancy sounding words to let everyone know that you know big fancy sounding words? So what this topic's about, it's about things that go back and forth, where the force that sort of restores them back to that starting position is proportional to how far to the side it gets pushed. We're looking at two very specific examples. This is kind of a specific sort of motion. And the two specific examples that we're going to look at are a simple pendulum and a spring oscillator. So a simple pendulum it's just a mass, which we call a bob. And that simple mass is at the end of a massless string. Now, no string is actually massless, right? Everything has mass. But it's kind of an assumption that we make to do the simple pendulum. If you're interested in learning about pendulums where the string does have mass, maybe sign up for AP Physics C at some point, where we'll learn all about it. So a pendulum is, just to make sure you know which word I'm talking about, it is none of these. There we go. It's just again, object at the end of the string, goes back and forth. That's it. That's what a pendulum is. It's at the length of it's at the end of some string with a certain length, and that's that. Okay, a spring oscillator is a mass at the end of a spring, and it'll kind of bounce back and forth. We'll start out doing just horizontal spring oscillators, but we'll add in vertical as this unit sort of goes on. Basically what I'm talking about is something like this. It's an object at the end of a spring, and imagine you pulled it to the side. It would kind of like bounce back to the other side, then the spring would push it outwards, and then the spring would sort of pull it back, and then it would sort of bounce outwards again. So that's what you're looking at when you talk about a spring oscillator. Yeah, all right, same thing. And that's that. Before, when I talked about the restoring force, this is sort of like a nice illustration of what I meant. The force is, see how the force is always pushing it back towards like that middle equilibrium position? That's what makes this what we call simple harmonic motion. It's sort of like the more basic example of something that has this behavior. Cool. Measuring the timing of oscillation. So we're going to deal with these ideas a whole lot, so I don't want to spend too much time on it today. But we are going to have to talk about the timing of this oscillation. So we measure the timing of something that goes back and forth, or something that sort of repeats in cycles, using two values that both measure the timing. We use the period of that motion and what we call the frequency of that motion. So what period is it's the time in seconds for one complete cycle. So what a complete cycle means is it's all the way out and back. It's kind of like I guess the way I'm going to phrase it here. Um, so to go out and back, what I mean by that is you take a position, and it's the time it takes for the object to go like all the way to one side, all the way to the other, and then back to where you started. So a complete period for like this motion would start maybe right now. It goes all the way out, and it would end here. One complete cycle. That was a certain amount of time went by there. That time is what we call the period. If you started timing when it crosses this middle line, what we call the equilibrium position, it would go, let's start now, all the way out, all the way to the other side, and then back to where you started. So that time would be a period. Time is represented with a capital T. I'm sorry, the period is represented with capital T. We've been using time as a T all year long. We use a capital T to show that this is the period. So it's like, it's not just any random amount of time, it's this period, the time it takes for one complete cycle. Frequency. Is the number of cycles per second. The number of cycles per second. So I want to be clear here. Period and frequency are both measurements of the timing. One is how long this thing takes. The other is how many of these things happen in 1 second. So these two are going to be kind of easy to confuse and to mix together. But we'll do a couple examples that I'm hoping are going to kind of clear it up. Frequency is, we use a symbol F for it, and we measure it in hertz. Now, hertz is the numbers of cycles per second. So let's say something goes back and forth 2 times per second. One way that you could represent that is 2, and then it's like 1 over seconds is the unit for frequency. It's 2 per second. Like there's no unit on top. It's just 2 per second. That's kind of annoying, and that's kind of just like a weird thing to look at. And so what we call that number of times something happens per second, we give it kind of like a shortcut, sort of an abbreviation, hertz. It's the number of times it happens per second. If something doesn't happen, like if it takes more than a second, you'll end up with like a decimal number of hertz. So it would be like 1/3 of a hertz, meaning 1/3 of it happened per second. It only got 1/3 of the way through in each second. We'll do examples, and I'm hoping we'll clear it up. Okay, the size of the oscillation, amplitude. Amplitude is a measure of the maximum displacement. For a pendulum, we measure amplitude in degrees. It's the amount of degrees to the side that the pendulum swings. Does it swing like very far to the side or very much not far to the side? For a spring oscillator, kind of like the picture that you saw, if we have an equilibrium position right here, it's how far that stretches. So we'll call it like A, the amplitude. A nice example is that animation we just looked at. Here the amplitude is, if you look at this dot, because it's a nice clearly defined thing, it looks like it goes all the way to the side of like -1 and 1. We would describe 1 as being the amplitude. We always measure amplitude from the equilibrium position. So the amplitude is 1 for this drawing, meaning it goes all the way down to -1 and all the way up to +1. That's the amplitude. So from equilibrium position. Relating period and frequency. All right, we get a new equation for this. Now, period and frequency are both measurements of timing. And so again, they can be very confusing. Since they're both measurements of timing, if you know one, you can always find the other. Because if you know the timing, as described by one value, you can find the timing as described by this other value. The equation relating them is in your AP reference tables. It is this guy right here. It's T equals 1 over F. We're going to ignore this middle part for now. That'll come up when we do our I guess waves isn't a topic for this year, but it'll come up when we do rotation. So for now, period is 1 over frequency. Period is 1 over frequency. If you're quick with your math, you may recognize that if you like kind of put this over 1 and cross multiply, you end up with this other statement. Frequency is 1 over period. So, you know, that's just a little bit of cross multiplication, a little bit of solving. So either one of these two different like equations to relate the two works fine. Just depends what you're solving for. Cool. So let's do some examples to try and clear this up a little bit. A pendulum swings back and forth 2 times in 1 second. What is the frequency? What is the period? So 2 times in 1 second. It happens twice per second. Now, something I'm going to bother you a lot about with this topic is the number of times something happens per second. The number of times it happens per second. That is what frequency is. It's how frequently it happens per second. So the correct answer to A is 2. 2 hertz. 2 times per second. That is the definition of the term frequency. The number of times it happens per second. Frequency is times per second. Cycles per second. Now for the period. If we know the frequency, we can always find the period using this equation up here. T is 1 over F. Okay, plugging in. 1 over 2 is... Well, I guess that's it, right? I guess I'll write 0.5 seconds. Now, bringing up like what these two things mean. If something happens twice in 1 second, that's its frequency again. That is the definition of frequency. It's the number of times it happens per second. Now, period is how long did it take to happen just once? It's a time period. How long did it take to happen once? Well, if something happens twice in 1 second, how long did it take to happen each time? Like a half a second, right? Because the first time took 1/2, and the other time took the other half, and that's your full second of motion. So the period is just 0.5 seconds, the time it took to happen once. Another way you can kind of think about it, if it helps, frequency is the cycles per second, and then the period is the number of seconds that happen per cycle. So another way of thinking about it, 2 times in 1 second, 2 cycles per second, which means that it takes a half a second per each cycle. All right, so for number 2, a pendulum swings back and forth 20 times in 1 minute. Determine the period and frequency. So if we think about this, we've got a time of 60 seconds. We've got 20 cycles, I guess you could say. How long did it take to happen once? Well, if you want to think of it as the period is the seconds per cycle, I mean, you could probably just think your way through this one, but I don't know, here's a way you can do it. Seconds per cycle, that's 60 seconds per 20 cycles, and what do you get? 3 seconds. 3 seconds for each cycle. And if you did that 20 times, you'd be a full minute. Frequency is, I think this one's probably the easier one to remember. Frequency is cycles per seconds. So if you have 20 cycles in 60 seconds, you get 20 over 60 is 1/3. And the unit here is hertz. Now, what does that mean? What that means is it takes 1/3 of a cycle happens per second. Put in different words, if it takes 3 whole seconds for this to happen, 3 whole seconds for this process to occur. So how many happen in a single second? Well, 1/3 of that, right? If it took 3 seconds to happen once, then, we only got 1/3 of the way through this after 1 second. Okay, and that answers our question. We found both the period and the frequency. So these two, it's kind of easy to get them confused, but we'll do a little bit of it today and a bunch when I see you again. I'd like you to do 3 and 4. Never mind, let's just do 3 together, and then we'll do the rest of these when I see you again. For 3, pendulum A has twice the frequency of pendulum B. Explain what this means. So what this means is if A has twice the frequency, kind of what it sounds like. It happens twice as frequently or twice as quickly. So A swings 2 times as fast. And that's fine. If you said that A took half as long to go back and forth or anything like that, that would be fine. All right. Yeah, 4 through 7 we'll do when I see you again. That way, we can go over this again in person. I can answer your questions and all that kind of stuff. Probably more important is these 2 new equations, calculating the period of an oscillator. So in addition to just describing the timing, like you should have a feel for that concept and what it means, you should also be able to calculate the period for one of these things, either a pendulum or a spring oscillator. So there are equations for both of these, and let's take a look at them. They're both in your AP Physics reference tables. They're kind of annoying to remember. Even I have trouble remembering these and getting them right sometimes. So these are your 2 equations for the period of a spring oscillator and the period of a pendulum. Pendulum got a little P for pendulum. Springs have a little S for springs. So it's kind of straightforward. And these questions will also be kind of straightforward, which is nice. The period of a spring is 2 times pi times m over k, the square root of m over k. For pendulum, 2 pi square root of L over g. So let's get these all in your notes so you remember, so you have them. T equals 2 pi square root L over g. They've got a script L, which is common when you write it. I just find that mine look like zeros or E's, so I'm going to go with capital L. Quickly, whoops. Oh, I'm sorry, this is the pendulum. Whoops. Okay, so let's give it a little P for pendulum. Okay, T stands for period, and the P just means the period of a pendulum. 2 pi are, constant. They mean 2 and they mean pi. L stands for the length of, more specifically, the string. So actually this equation may look familiar from the lab we did last week. I kind of asked you to design an experiment around this equation. We're going to measure the length of the string in meters, and G stands for the acceleration due to gravity, which we measure, as always, in meters per second squared. Now the thing to point out here is that the period of a pendulum is not affected by anything that is not in this equation. For example, mass is not in the equation. If you have a mass at the end of a string, the value of that mass, how much mass it has, does not affect how much time the pendulum takes to go back and forth. Which kind of makes sense because we learned that, if you think of a pendulum as like gravity causes it to accelerate, think of this as like an application of free fall. We learned that mass does not affect the rate at which objects fall, so that kind of makes sense. Also interesting, the amplitude does not matter. So this angle in here is the amplitude of oscillations, how far to the side the string goes. It doesn't matter if you pull it to the side a little bit or a lot. Man, this thing isn't working. A little bit or a lot. It'll have the same period either way, which is kind of neat. Although it is worth pointing out, this equation, for reasons we're not going to get into, only applies to small angles. So if it's a large angle, this kind of breaks down a little bit. My pen's not working. This is awesome. There we go. For a spring, T spring, and again, you do have these right in your reference tables. 2 times pi times m over k. And it's worth pointing out that where the mass did not affect the period of a pendulum, it does affect the period of one of these spring oscillators. So just like before, T stands for period, M stands for mass. Oops, let's get some units in here. Measured in seconds, measured in kilograms. And lastly, K stands for the spring constant, which we measure newtons per meter. Some of this kind of makes sense if you think about it. Like for the mass, imagine that this block was like very massive or like very heavy. That would be hard to move back and forth. It would be hard to like change the direction that it's going in and then pull it all the way back. So mass would make it take longer, right? It's like if I asked you to shake something back and forth, if it had a lot of mass, that would be hard to do, right? It would take you you'd have difficulty doing that. It would take you a long time. And so a large mass gives you a longer period. Notice mass is in the numerator of this fraction, meaning that there's as this goes up, the period will go up. Now K, the spring constant, remember that's like how strong the spring is. So a stronger spring is able to sort of snap this mass back and forth much more quickly. Cool. What do you have to be able to do? You basically have to be able to work around these equations. Identify things that matter, like length for a pendulum or mass for an oscillator. And you also need to be able to identify things that don't matter, which is like the amplitude for both of these, actually. Kind of interesting. Doesn't matter how far to the side you stretch the spring. Turns out it'll have the same period. So let's go. We'll do, oh man, how long are we on this video already? 20 minutes. All right, let's do 8, 9 together. You'll try 10, 11 on your own, and then I'll stop bothering you and let you work on the question. A pendulum is created when a mass connected to the end of a massless string and pulled to the side. The pendulum oscillates with frequency f0. The string is cut in half and the pendulum is set into motion again. In terms of f0, what is the frequency of the new shortened pendulum? Okay, so I really don't recommend that you try to memorize any of these. Now, it's asking about frequency, and I do want to point out neither of these equations deals with frequency. They both deal with period. But if you know the period, you can always find the frequency because t is 1 over f. So, and then actually if we flip-flop this, because we're solving for period, you get we're solving for frequency, you get f equals 1 over t. So here's what I'm going to do. I'm going to figure out what happens to the period of this pendulum. T equals 2 pi square root L over G. And I'm hoping at this point in the year, this phrasing of something halves, something doubles, that kind of thing, it should start to sound familiar. We have a factor replacement method for that. Figuring out what happens to the period. 2 and pi do not change, so I'm just going to replace those with 1s because they're constants. They're the same each time. Times the square root of, it sounds like we halved the length of the string. And did we change the value of gravity? No. Oops. So I'm going to replace that with a 1. And what do you end up with? 1 times 1 is 1, times the square root of 1/2. Basically, there's a lot of fillers and placeholders here. You get the square root. Man, this thing's the worst. The square root of 1 over 2, which is 1 over rad 2. Now, that is not the answer to the question, because this is what happens to the period. But the question asks what happens to the frequency. So I'll point out that we made the length shorter, which decreases the period, right? 1 over rad 2 is about 1.4. So 1 over 1.4 is a fraction. It's a smaller number. Now, the period is shorter. It takes less time, which means it'll happen more frequently. Saying that again. It takes less time and will happen more frequently. So, plugging in 1 over rad 2 as the period, okay, I'm going to kind of go into over here. 1 over rad 2. All right, dividing by 1 over rad 2 is the same as multiplying by rad 2. And so the final answer here would be rad 2f, or rad 2f0, I should say. We'll do more examples like that. Number 9, then I'll have you try 2 on your own. A spring oscillator with spring constant k. All right, so I'm just going to write out my equation just right away. 2 pi square root of m over k. Is displaced by an amplitude, causing it to oscillate with period t. The mass at the end of the spring has a value m. How do the following changes impact the period? Answer in terms of t. Okay, so when I say answer in terms of t, meaning the answer is going to be 2t, 1/2 t, 4 times t, that kind of thing. All right, the amplitude is changed to 4a. You have an equation here. Just follow the equation. Is amplitude part of the equation? No, it's not. So the answer to this is t, meaning it'll be the same. That's it. Amplitude does not, again, it doesn't factor into the equation. You don't have to do it. The mass is changed to 4m. Okay, so mass is part of the equation, so I'm going to go do my factor replacement here. T equals 4 I'm sorry, 2 times pi times the square root of 4 over 1. And I got that by just doing, stays the same, 4 times as big, stays the same. And you end up with 1 times 1 times the square root of 4, which is 2. 2t, 2 times as big. If b made sense, then you might see where c is kind of going. But plugging in, t is equal to 1 times the square root of 1 over 4. All right, 1 times the square root of 1 over 4 is just the square root of 1 over 4, which is 1/2, or 1/2 t. So just factor replacement. Just need to, identify things that aren't in the equation, like, an a, if that's what's happening. And they will ask that a lot. Or maybe do your factor replacement if it is in the equation. All right, I want you to try 10 and 11. I'll give you please pause the video, try them. And if you get stuck, just hit play and we'll go over it. Okay. Should have paused the video there and went through it. So let's see what we got. Now, I'm asking a very, very similar question, and the equation itself is very, very similar. Let's go. We changed the length to 4L, so I'm just going to do that factor replacement. T equals 1 times the square root of, length is 4 times as big. All right, 1 times the square root of 4 is 2. 2t. So this pendulum, as it goes back and forth, will now take twice as long to go back and forth. The mass is changed to 4m. So this problem is trying to do two things. One is confuse you into thinking mass has something to do with the pendulum. The other is to confuse you into thinking this is like a spring oscillator. Mass is nowhere in the equation. The answer is t, meaning it's the same. Done. So be able to identify things that are not part of the equation and sort of be confident that there's no effect here, because that is something they're testing. And in the same way, the amplitude is 4 times as big. I don't see a theta in that equation. I don't see an amplitude in that equation. The answer is t. It does not matter. All right, lastly, 11. A student is doing an experiment to determine how the mass attached to an oscillator affects its frequency. To do this, the student, I think this is supposed to say sets up. Sorry about that. Sets up a spring oscillator and a simple pendulum. The student attaches a mass m to 2 oscillators, then attaches 2m to both oscillators. When the 2m mass is attached, is the frequency of the spring oscillator greater, less than, or the same? Okay, we don't have an equation for frequency. I mean, I guess you could solve for it, but let's just do this. Square root of m over k. If you, follow me on this, so if we increase the mass, so if m increases, then looking at this equation, t will increase. What does that mean? Okay, well that means that it takes longer to happen. If something takes longer to happen, let's think back to frequency now. Frequency is the amount of times it happens per second, times per second. So if it takes longer to happen, what will happen to the amount of times per second, or cycles per second? It will decrease. If you're a little bit, more of a mathy type person, period is 1 over frequency. Frequency is 1 over period. You'll notice that these two values vary inversely of one another. Like if one goes up, the other will go down, which kind of makes sense because, again, one is a measure of how long it takes. The other is a measure of how fast it happens. So if you can figure out what happens to the period, you can always figure out what happens to the frequency, because it'll be kind of like the opposite effect. These two sort of have to vary inversely by definition. So is the frequency of the pendulum greater than, lesser than, or the same? Well, pendulums, and we're going to be careful here, do not have a mass component. So the answer to this is the same. Because again, it's just not part of the equation. Okay, that's it. I'd like you guys to spend the next period working on the quest. It's, I know I wasn't there for this, so I can't help you with it. So I tried to keep the questions very, very simple. Feel free to work. I mean, I know it's hard to work together, but feel free to work with one another. I don't know, set up Discord or your own separate Google Meet or whatever it is you guys do to try and get through it. I tried to keep the questions fairly simple. If you're really having trouble with this, if it's really going bad, I'll be in, I don't know, soon, I hope, and we'll figure it out.